Okay, I guess
Yeah.
that problem is fixed. Maybe
Yeah.
we should get started.
Yes.
Um, Perfect. Good afternoon, everyone, and welcome to today's AMD seminar. It is my great pleasure to introduce our speaker, Eva Tardos. Eva is a Jacob Gould Sherman Professor of Computer Science, currently the chair of the Department of Computer Science for a second term after being chair between 2006 and 2010. She was interim dean for computing and information sciences, and more recently, she was Associate Dean for Diversity and Inclusion at Cornell University. She received her bachelor's and PhD from Eötvös University in Budapest. She joined the faculty at Cornell in 1989. Tardos's research interest is in quantifying the efficiency, algorithms and interface of algorithms and incentives. She's most known for her work on network flow algorithms and quantifying the efficiency of selfish routing. She has been elected to the National Academy of Engineering, National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, and to the Hungarian Academy of Sciences. She is the recipient of a number of fellowships and awards, including the Packard Fellowship, the Gödel Prize, Danzig Prize, Fulkerson Prize, ETACS Prize, and the IEEE von Neumann Medal. She co-wrote a widely used textbook, Algorithms Design. She is editor-in-chief of the Journal of the ACM, has been editor-in-chief of CM Journal of Computing, and editor of several other journals, and was a programming committee member and chair for several ACM and IEEE conferences in the area. Eva, we know that you are busy and we very much appreciate your joining us today. We are excited about your talk. Maybe we can switch to your slides, and in the meantime, I have a quick announcement for the audience. During the talk, if you have any questions, you can type it into the chat and I will relate to our speaker. Alternatively, if you raise your hand, I'm going to unmute you so you can ask any questions directly to our speaker. With that, Eva, the floor is yours. Thank you so much for joining us today.
Well, thank you for everyone for coming for the talk, and I apologize the unfortunate conflict with the EC deadline. I hope everyone is managing to still finish the EC papers in the remaining time. I'm going to talk about some of the things that Ozan introduced me for being caring about is price of energy and in some version of routing. I guess I want to combine this with learning and maybe some features of queuing system, and everything I talk about is joint work with Jason Gaitonda, and I'll tell you the papers they came from as we go. Oops. So I see. Again, one of the main things I has been for a long time like thinking about is traffic routing, congestion in traffic routing, and congestion causing delays. And there are two prime examples of this sort of where this is a model that has been used. Is one is car traffic and the second one is packet traffic. In both cases, it's reasonable to think about the learning model. The routers or the car drivers are, as time goes on, repeatedly participate in this game that they have new packets or new days they need to drive, and they need to figure out what is the right way to go. So I guess the basic model for most of this talk will be a repeated game where agents are learning. So agents play a fixed game. This can be auctions, but in the context of this talk, it's more like routing. They selfishly aim to minimize their cost or maximize their reward. They use some sort of learning, and the model of learning in most of this talk will be no regret learning. And here is what sort of it's trying to model is that players maybe show up, maybe they know something, maybe don't. I'm neutral about this. But after they played long enough, they have some better idea. And I'll come back to this again, but I guess the no regret criterion, which maybe most people are very familiar with, or I hope many are familiar with, is a standard of learning. Like it is easily possible that, on minute number 17, you should drive this way. And on Tuesdays, on the first Tuesday of the month, some other way. And that's very complicated. And you can't, or I don't expect you to be able to learn to compete well with that sort of benchmark. I'm offering you a very simple benchmark. If there's a single choice X, I guess in this case, a single rat X, that historically has been very good, then you have two good options. Either you're alternating between many other things that are doing better this X, in which case you're happy as is, or if X is so much better than what you're doing, please wake up to this and switch. And that's what the no regret benchmark is. It's asking you to do at least as well as any single choice with hindsight, plus a little bit of error, which we call regret error, which, coming from the fact that initially you didn't know what is the right choice. The requirement for the regret error is that it's not going linearly this time. In the worst case, there is a kind of root t, that is over time t, the regret error only goes as root t, and depending on what information I'm feeding you, you might be able to do better than this. That's going to be our behavior model. I guess there are tons and tons of literature all telling us that no-regret algorithms are not so hard to come by. The ones I'm citing here differ in the simplicity or naturalness. I guess the original Hanan paper was just existence that such an algorithm does exist. The further ones are all rather simple natural algorithms. But what I want to point out that I'm not making the assumption that anyone will follow any of my named algorithms, rather making the assumption that they satisfy the condition. That is, I want to think of this as a behavioral assumption. Roughly speaking, no matter what algorithm or non-algorithm you followed, if there was a really good choice, reasonable people or reasonable systems wake up to this choice and try to do at least as well. So I'm thinking of this as a behavior model and not as an algorithm. So I don't care which of these algorithms you like or whether you like any of them. There's some evidence in the auction literature that behavior at least in auction setting, reasonably close to satisfying this criterion. In this work, I'm going to use it as a behavioral model in a theoretical work. And finally, of course, it's always good to point out that this assumption is less restrictive than assuming that they somehow settle on a one-shot Nash equilibrium of this repeated game. If they are repeating the same action over and over again, and then if that action is a Nash, then clearly they will satisfy that no single other action is better for them. This is exactly the Nash criterion. So what this does is gets rid of the stability assumption of Nash and only keeps the you don't regret switching to other things assumption. So that's going to be the basic assumption for most of my talk. I do have a part at the end when I'm actually myself criticizing this assumption and offering alternatives. I'm happy to entertain questions now on anything, or in particular on you not liking the learning assumption, but maybe it's better to table it when I show you other results which are actually natural criticism of this assumption, but happy to not wait. So the question I'm asking is social welfare and the price of learning and the price of energy. Again, hopefully most people have seen this, but the contrast we're coming from, there's at this point growing and beautiful literature originally started with Koutsoupias and Papadimitriou, which is asking, how does the social cost of a Nash equilibrium outcome compare to the social optimum? That's not exactly the question I'm going to ask, but instead I'm going to ask, I think, a bit more practical question than that, which is the alternate question of how much extra resources do I have to give to the system to do as well via Nash equilibrium or via learning as had I been able to coordinate it? That is, how much extra capacity you need in case of routing or in case of whatever, how much extra resource do I have to give you so that I can let you behave selfishly and it's going to be fine for the system. For both of these classes of known results, there is a beautiful extension originally studied by a paper of Blum et al., but maybe championed by a very nice paper of Tim Ravgarden that says that our proofs for this price of energy results were so simple and uniform that they naturally extend to learning outcomes. That is, as people learn, they're going to not necessarily reach Nash equilibrium. In sometimes many cases, the auction setting they tend not to, but whatever we proved about the quality of the solution is also valid for the quality of learning outcomes. So the price of energy also applies to learning. Okay, this was a really quick preview of sort of the background, and now comes the criticism. All these papers make a very critical assumption that is, every time you repeat the game, you're facing a new copy of the same game. That is, more importantly, the red line here, no carryover effect between runs. So let me try to emphasize what do I mean by examples, and which examples is it reasonable or unreasonable to see this. So our two examples in routing were morning rush hour and the second by second traffic patterns on packet routing. And morning rush hour, this is very reasonable. No matter how bad traffic was Monday morning, by Tuesday morning, everyone somehow managed to get off the road. There is a lull in the middle of the night that clears the traffic. But it's not reasonable in second by second traffic on the internet or actually on cars. If in millisecond number 17, there were lots of packets on a particular router, millisecond number 18, they're all there, and they're equally congesting that router. So there is leftover effect due to congestion in some minute. The next minute is equally congested just because the very same packets are still there. So there is a leftover effect. And I think one real handicap of the existing literature that it's ignoring or not modeling this leftover effect. And I think a big open area that we're trying to contribute to by this paper, actually a sequence of two papers that I'm going to tell you a little bit about, is trying to model this in a very simple setting, but with carryover effect. So that's my goal here. What I'm going to do next is actually show you or discuss the model that we're using, which is a very simple model of routing, and then try to show you what examples of that model and what we can prove about it. And again, let me repeat the comment that Ozan made in the beginning. I'm very happy either clarifying or even any form of questions in the middle of the talk. Please either speak up or type it in the chat window or whatever the best method for questions is. So if there are no immediate questions, then let me show you the model I'm going to use. So the model is a very simplistic version of routing, which I think is better be called a queuing system, but even a simple queuing system. There are a bunch of queues and a bunch of servers. The queues will get packets and some, rate. I guess lambda will be the rate at which they get the packet. Lambda I for QI is a Bernoulli process where a new packet shows up and they want to get its service. The servers naturally have a service rate that's, standard from queuing theory. Each of them, server J has a service rate of mu J. That's maybe will be his probability of being able to serve a packet. What will be the game theory here that each queue will, every time step, will take one of his packets and send it to one of the servers. So there is a serious limitation here, which is valid in internet packet routing. The routers, even though they connected to multiple servers or multiple other routers, they all have to choose one and send that one because, sending is an activity that the router has to focus on or concentrate on. So they take one packet, send it to one of the servers, and the choice they're making, which will be game theoretic here, is to which server is good to send to. Now the servers get all these packets. They will try to serve one of them. Again, they can service multiple packets. A packet can either succeed and get served or not succeed, either because the server failed or because there were multiple packets sent there. Like, for example, our top server here has this problem. There are multiple packets coming in. And I guess the leftover effect, and the particular way I'm going to model leftover effect, is that leftover server packets are sent back to the queue that sent it to them, and you're going to have to resend it. And then finally, last but not least, I promised you up front that there's no regret learning here. I'm going to assume that the queues are using a learning algorithm to figure out which one is the good server or which server they have success at. Yes, happy to take questions.
I have one quick question. Actually, one clarification question and one positioning question. So the clarification question is the following. If I followed you correctly, the queues can submit jobs to any server. There is no restriction in terms of the action set, if you will. Is that the case?
That's true in our simple model. You're right. The natural extension would be to only allow each of them a subset that they can serve. But the simple model we're using, everyone can send everywhere.
Okay, that's clear. So the other question that I'll ask is the following. This setting reminded me of settings in communication systems. So you have multiple transmitters using a message channel to submit their messages. If multiple of them send at the same time, there's a conflict and the message is not relayed. And then they have to back out. They have to be silent for a random amount of time so that they can actually succeed with the transmission. This is a vague, high-level question. I'm under the impression that in that line of literature, people have not really explored the game theoretic effects, or I don't know of any. But I know that there are papers that look at having multiple channels and the transmitters exploring different channels. So is there a connection between the two lines of work?
Yeah, they did explore game theoretic effects to some extent. One version of game theoretic versions arises there even if there is a single server only,
right,
which is not going to be in our case. Like if there's a single server, you might as well send to it. There is no hard handicap. In their version, if multiple, I can go back there, and if multiple packets go to the same server, both of them get sent back. Neither of them succeeds. So then there is an extra option there. You might not want to send anything because decreasing your service rate helps
clear the congestion
behavior. Now, one problem is in those models, and actually just stay with the single server. So in our model, a single server, it is in your interest to always send. In their model, in a single server, it's dominant strategy for you to always send. It is dumb, but it's dominant strategy. So this sort of simple way of thinking selfishness, you want the other guy to back off, you should just send. So there they have to be careful of what exactly do I mean, what's the best rate, what might be a cooperative thing to do. But just to use the either no regret or actually a Nash, it is dominant strategy to send. And so doing a game theoretic analysis runs into, you have to use other notions of what you meant. And there is literature that does that. In our setting, there isn't this problem because something gets served anyhow. And therefore, a game theoretic analysis is clear and very doable. Does that help? Yeah. Okay. So again, the question we asked, yeah.
So I wanted to ask one follow-up clarifying question. From a server's perspective, all queues are symmetric. So if I get from Q, I, and I prime, I don't care which one I'm serving?
There is an excellent question, which is maybe sillily not on this slide. It will come back. There is a question of what policy should the server use. Mm-hmm. And we'll have results to say that if you do this policy, then this happens. If you use a different policy, you're better off. So I'll come back to your question. But indeed, I didn't resolve of which packet gets served. And at least for our competition from the queues, the answer to this is very important. The answer is very different depending what the servers do.
Great.
So great question. Okay, so the question we're asking, as I promised, is how much extra capacity do I need to give the system to be able to succeed when people behave selfishly and I didn't manage to coordinate them or didn't try to coordinate them. But before I go there, I want to start with some super simple examples to have people feel more comfortable about the model. So the simple example is a single server, single queue. There's nothing strategic, no choice. Everyone just sends, and we all know this from very basic queuing theory. If lambda, the arrival rate, is less than the service rate, then queue sizes will remain bounded. If lambda equals mu, then they don't, and lambda is bigger than mu, then you have linear growth. This is sort of, we'll see the analogs of these results, but it's good to remind you that that's the baseline. The second baseline is still no competition, but now there is learning, single queue, multiple servers. So this actually was studied by a paper of Krishnaswamy, Sen, Johari, and Sakotai in NIPS 16. And what they did, first of all, the condition is easy because the queue can only send one packet at a time. Obviously, he should send it to the best server. The only trouble is he might not know which one that is. And what the paper and the studies in the paper is using a no-regret learning algorithm to find the best server. What will happen is that the queue behind this queue will build up while he's struggling to find the right thing, and then go down when he found the right thing. And they've studied how high the queue goes before it goes down. So what exactly is the evolution of the queues? So what we're doing next to this is adding competition. That is adding the fact that there are multiple queues in multiple servers. They actually have some results on multiple queues and multiple servers, but not in a competition setting. So I'm going to skip that. So remember, our question is, how much more capacity do I need? And to that, I need a baseline. What is my baseline? How much would I need if I were to coordinate them? And let me tell you what the baseline is, which I think is very natural and hopefully become very believable for everyone. If I number my queues and servers so that the arrival and service rates are monotone going down, then the following very simple criterion hopefully is very naturally necessary and in fact not hard to prove, it's also sufficient. The necessary condition that if I take the highest arrival rate top k queues, take top 3 queues, then combined, these 3 queues can only use 3 servers. The best they can do is use the 3 best ones. And that the service rate of those 3 servers should be greater than the arrival rate of these queues. Like, for example, if the top arrival rate queue should be less than the top service rate of the best server, the highest arrival rate 2 queues should have less arrival than the best 2 servers, and so on for every k. It's not very hard. This is obviously necessary, and it's not very hard to prove that this is sufficient. So what we're asking, how much more beyond this do you need? Because you don't have the power to coordinate them. Here is what we proved, and now I come back to your question about packets. We consider 2 versions. Option 1, the maybe most natural one, uniformly random. And option 2 is something that definitely is there to help coordination, oldest first. That is, allow packets to carry a timestamp on when did they show up and favor the ones that have been waiting for a long time. And what we're proving is that uniformly random is really bad. And I'll show you an example of this. Uniformly random, virtually no matter how much more capacity you give to the servers, it's not enough. Selfishness ruins the system performance. In contrast, time really helps. If with the timestamps, that is oldest first, you have to up the service rate by a factor of 2. But if you have twice as much service rate, then what would have been needed for central coordination? Then learning agents coordinate enough that they get all the queues through. And this factor of 2 will turn out to be actually sharp here. So you do need the factor of 2. So again, this is the result. What I'm planning to do next is, first of all, I wanted to show you what's wrong with the uniform arrival because it's a simple and intuitive example. And then I want to give you a little hint of, or some amount of outline of how the proof goes. And as I promised, I want to talk a little bit about the new results we have, which in particular also criticizes the no regret learning assumption.
There's a quick question in the chat.
Sure.
Eva, let me just relate to you. Do servers know the size of each queue? If not, could queues signal to the server how backed up they are?
This is actually a great question, and maybe a sort of, let me take it a bit more broadly. To get our results with the factor of 2, they don't need to know anything. Neither the learners nor the, so the moral question is, who knows what? So I can start with, what do the learners know? To get the results we're claiming here, all they need to know is whether the packet came back or not. So from a learning perspective, this would be a low information setting. You don't know what would have happened on other queues. You don't know why your packet was returned. Is it that the server failed, or is it that the competition was too big? You don't have to fed any information. You just need the one bit. Did your packet came back or not? If I feed you more information, obviously you can learn better. It does help you learning. And one thing that's swept under the rug in all of my slides, I only say that that this amount of capacity allows them to get all their packets through, which in more mathematical term will imply that the queue sizes remain bounded. But the band will depend on how much information I fed them. So that's actually not the question you asked, because it's the knowledge on the queue size and not the knowledge on the server side. The knowledge on the server side, I guess assuming that timestamp is what they use the servers to decide between packets. In some way, I think what you're suggesting is the queue length might be something they could use as serving the queue, that packet that came from a queue that has a very big queue length. I intuitively believe that that's very analogous and probably works just as well, but technically our proofs are written out for the timestamp version. And I see there is one more question there. I don't know if, no, maybe not.
I don't think there are any more questions. Yeah. I think they're answered.
Okay, thank you. Okay, so again, the plan is to show you what's wrong with uniform random, because I find the example simple and intuitive, and then give you an outline of how does one argue about this system. Offset again, using the wrong forward. Okay, so here's the example of where uniform selection is problematic. At the moment, I'm building in a slack of C. You can think of C as an arbitrary large constant, but actually I can make it polynomial also, and it's equally problematic then also. So with the constant, think of arrival rates on the left-hand side are these lambdas, and each of them have a matching Q on the other side that's a factor of C higher capacity, higher service rate than the arrival rate. So if they were only just sending to their own personal server, everything would be fine, because the service rate is factor of C up from the arrival rate. So we're serving everything. But, savage people won't actually do that. And that's the whole point of this. A whole bunch of them will see that there's this amazingly good server. Why wouldn't I use that? And in fact, they're getting their packets served faster. They don't need that because the arrival rate's pretty damn low, but they get a better service, and enough of them switch up that the first queue up there with the high arrival rate is in trouble and will never get served. And timestamps really help, because once this starts happening, the first queue will have very old packets and therefore take over the server, and life will suddenly become good again. So that's sort of where the intuition is coming from. So let's now go on for the sort of actual theorem that we wanted to state, and it's a bit more formal here. So the servers do all this packet first. Queues use an no-regret learning algorithm. We satisfy the capacity constraint with a factor of 2 blow-up. And the claim is that when that happens, all queue sizes remain bounded in expectation uniformly over time. And for this result, the factor of 2 is tight. And I can admit again that we do actually have a band of what bounded means here. And that, of course, depends on what form of learning did you use. So better learning will result in smaller bands. So I want to give you an idea of how does one prove such a thing. And I guess maybe not too surprisingly from queuing theory, you want to use a potential function. And so maybe the main idea is the name of what the potential function is. And the rest is, maybe interesting, but it more naturally follows. The potential function that gives us the intuition is this following thing. Phi tau is the number of packets that are tau age or older. And then my actual potential function is the sum of phi tau for every tau. So that particular means if a packet is 18 time steps old, it's going to contribute 18 to this potential function. So sum of time steps of all the packets in the system. This is a good potential function because if I were to prove that this potential function stays bounded, then I'm home because that the queues, obviously, the timestamps stay bounded and therefore the queues had to stay bounded. The main tool we're using is a beautiful and elegant theorem from probability theory that says that if you have a function phi of a random process and the following two conditions hold, then it will remain bounded in expectation. And I guess maybe the second is the more important condition or more natural condition. It has to have that whenever this phi function is high enough, it has a negative drift. Obviously, I need this. If this function is high enough, it still has a positive drift, then I guess it's going up to infinity. We know that. But if it's above some band, it always has a negative drift. And it's sufficiently regular, which actually will mean that it has bounded moments. Then it has then it will stay bounded. And I guess what I have to do to give you a sense of how this is useful is to connect the two things I assumed, no regret learning and a factor of 2 slack in capacities, should imply the negative drifts when they're large backups. The sufficiently regular condition is maybe more technical and will mostly swept under the rug, maybe not exclusively. So why do I like this potential function? I want to focus on a single tau, and then I guess in the analysis I have to put them all together, but some large age, and maybe there are some old packets in the system, tau old or older. The point about this, that because I give priority to old packets, this group of packets as a group has priority. Like if any server gets any packet from that group, it will attempt to serve one of them, not something else. So I'm going to look at a reasonably long window and look what these queues are doing that have the old packets. And I say, okay, there are two options here. Option one, that they're sending to the best servers. That's cool because, they have priority. So I don't know which one of them gets served, but some of them will get served here. So life will be okay. Option two is that they unfortunately didn't know to do that. And then I have to claim that when that happens, if they didn't do that, no regret will help me out. So to do this, actually, let me do a bit of a retour and remind you what no regret said, and actually more precisely turn the no regret condition into one that is in our current setting. So the no regret assumption says that they're not regretting not switching to a single queue with hindsight. So here is the assumption, like I guess they came and after this long enough window, hopefully they knew what to do. And every player for every fixed action, which is sending to a single queue over this time term horizon, has this inequality. And all I had to do is, because the goal is to clear packets, that's a utility-based goal, I had to turn the inequality around. So what they got across, that's the utility, is at least as big as what they would have done had they sent to a single queue, minus a little bit of error, which again we call regret. And again, it's roughly root t for time t. That's the condition. And that's what I want to use here. So going back to the previous slides, I claim that the no regret condition clicks in. So suppose they're not sending to the best queues. But the best queues, if they're not sending to the best queues, then wait. The next queues are possibly serving nothing or serving younger packets. They would have had priority. They should regret this. Or maybe they're not regretted because they're actually doing very well elsewhere. So regret guarantees that if they're not regretting not sending to these queues, these servers, then it must be the case that they're doing very well elsewhere. And that's what gives me the power. There are some extra technical details that I mostly will continue to keep it under the rug, but just to admit to you what they are. I argued about the period of a large no-regret window and talked about doing well on the no-regret window. I need a version of no-regret that's true for every long enough window, not just from beginning to end. Indeed, no-regret algorithms easily can adjust to this. This is a queuing system, an infinite queuing system. Arbitrary, unlikely bad things will happen because small probability items do happen. So what I have to argue that you recovered from this. So even a bad thing happens, I can start the window from that bad moment, and indeed, you still have negative drift. I had to talk about this. I said I sweep under the rug the technical condition about the bounded second moments. Unfortunately, my potential function that I claim to you, which is more intuitive than the one on this slide, doesn't have bounded second moments. So technically it's not working. I had to switch to an alternate potential function that is intuitively the same and very close to the same, but uses the deferred decision ID. Instead of every queue knowing how many packets it has, I will only remember what's the age of the oldest packet and try to express the expected length of the queue from that old age, which is what I did here. And that expression, that potential function has bounded second moments. So maybe that's a technical difficulty. And then finally, you apply concentration bands and the result follows. Again, there's some further technical details maybe still swept under the rug, but I definitely unhided the important ones. So I think the sum of the ages of the packets is a much more intuitive function than this somewhat crazy looking alternate function here, but they're approximately expectation, they're the same. And this one has bounded second moments. So it technically works in the proof. So I'm going to stop here with the proof, and the only part of the talk left beyond leaving you time for questions is what I promised in the beginning, a very quick preview of a new paper that we're in the process of writing, or kind of almost wrote, which in particular is important to emphasize or highlight here, because it comes with a discussion of, was no regret learning the right notion here? Or maybe that no regret learning is not the right notion. So
can I ask you a quick question?
Sorry. Oh yeah, definitely.
Before moving on to this next part, can you give us a bit of intuition where that factor 2 kicks in because of this no regret learning aspect? So you mentioned
it's a nice question. I guess I can offer you two different answers. One is, where am I using it in the proof? And second, a little bit about what the example is like. I do the proof because that's maybe easier to point out of where am I using it in the proof. I was thinking of, when I said that, what are these queues doing with the old, that have the old packets? I imagined something, or the proof imagined something that's highlighted on the picture, that these are the old queues here with lots of packets them, and they're sending to the server, each of them sending to a different server, or at least maybe some of them send to the same server, but this very natural way of having them sent to the top servers, when I want to say something of the form that either they send to the server is very empty, it's easier to argue if sending to the server is enough for me if they fed the server half filled it. Either they sent half to that server, or the server is half empty, in which case that other half that's empty offers them priority. That's a natural source of 2 in a proof. There's lots and lots of proofs of this form that lose the factor of 2 in the very same place. either I used half the capacity of these servers, in which case I should be okay, or half of it is empty, in which case they had priority and they must be doing somewhere else well. But for which this argument, it has to be that using half the top server, half capacity on the top server is good enough for me. So that's where the proof has the half factor of 2. The example is definitely a bit more complex. And originally we just had the proof, but the proof using the factor of 2. But actually, it ends up being pretty similar to the example we had here. So I can be playing a bit more with this example and definitely much more careful with the numbers and the analysis. One can set up a very similar system where even with the old packets, you do need the factor of 2. It's again, one large queue with large sending rate and a bunch of small ones. And what you have to be sure that the small ones don't and there's one good server, and the natural solution is the server to go like the packet to go directly to the server. And what you have to worry about is whether the small queues in their selfishness, can they outcompete the big one? So the setup is very, very similar to this example. It's a bit harder to set it up.
Great,
I hope
thank you so much.
Helps.
No, that was great. Thanks.
Other questions? Actually, this is a great moment to ask questions. So if there are other people want to ask questions, I should definitely give people a chance. So if there are no direct questions, one issue that always shows up in me talking about it is regret the right notion. And in some way now I'm convinced that it's not really, and maybe I should show you why. And then certainly happy to take further questions after that. So here is a very simple bad example. Why is this example bad? So 2 queues, arrival rate bit above 50%, a perfect server, which always serves something, and a kind of not so good one. And I made the numbers pretty close to each other. You can change them around a bit. So what will happen if you use no regret learning, or if you use a single shot Nash equilibrium notion even? The top server is literally better. It's dominant strategy seemingly to use the top server. Because even if they both go there, okay, maybe not dominant strategy, but kind of dominant strategy. Even if they both go there, there's not enough service capacity here, so they're going to have the queues build up like crazy. Slowly but surely, there'll be very large queues. So they're going to send every single period, but you get a 50% acceptance rate because the two of you are pre-equivalent, are competing. So you get across half of the time. And I made this 49 on the second server a lower number, so you're better off on the top server. And again, I can separate the numbers more if I want to. So from the instantaneous feedback version, the way no regret learning is learning, that is looking at instantaneous feedback, the top server is just dominant. No matter what the other guy does, you're better off on the top server. If you look at our satisfiability condition, of course, if I only coordinated, they could be able to get across because, twice 5.51 is just above 1, and the server capacity is 1.49, way above the little bit. So they could get across, they're just not doing it. What can I do to help them? Well, it turns out they can help themselves if they only are a little less myopic if they evaluate things. So suppose this orange queue decides that, I'm going to send some of my packets to the lower server. Not all of them, just some of them, a little bit. Every now and then I send to that one. Turns out they all get across. Turns out they both better off. Now, something weird's happening here. They're both better off, but because of our notion of no regret, this orange guy thinks he has a lot of regret. He should have regret. The best he can get out of that 49% success rate server is 49%, which is not enough. So the reason he's getting across, because as it turns out, he's aging a bit faster than the other guy is aging. These packets tend to be a bit older, so he actually gets priority on the top server. But that's happening because he's using the other server. He's not, like, there's something that's happening to him because he did the wise move that rather than always competing on top, sometimes actually willing to use the bottom server. You don't have to move much down to get across. It's easy to work out the arithmetic. He moves out like, I don't know, a quarter of the time. That's plenty. Much less is enough also. So the main message here is that non-regret learning is just too myopic. It's evaluating whether you succeed in measuring instantaneous success rate. If learning would instead take into account, okay, if I send, say, a quarter of my traffic to the lower server and only 4 quarters up there, what's my success rate over a long period? He would have discovered that it's better for him to send to the lower server. So no regret is too myopic, too short-sighted, and it's not actually the right learning policy. I can ask you the question of what is the right learning policy, and honestly, I don't know the answer. I have some proposals of what it might be, but maybe I'm going to not emphasize that. I can tell you what we can prove, and I don't have a learning results. What we can prove is if I, instead of looking at learning, I go back to the notion of Nash equilibrium, but this time looking at long-term success. So the Nash of a game in which you choose, which servers to send what percentage of the time and evaluate your success of what's good, not in the instantaneous feedback, but in the long-term success rate. The Nash of that game only needs 1.56 increased capacity, that is E over E minus 1 to be concrete. This band is tight also. That is, the extra service capacity you need if the learners are a bit smarter and don't look at the myopic feedback, but instead look at long-term feedback, you actually need less extra capacity for them to succeed. And I'm going to stop here and maybe tell you sort of what I hoped you to take home, you learned from this, or what I'm trying to tell you. Maybe my biggest message that learning in repeated games has very nice, attractive features and nice literature, but is avoiding games that have some carryover effect, where one iteration of the game has direct effect on the next iteration beyond what you learned from it. And that's an important open direction. We did offer a very simplistic Q model in which we can prove something, in particular, how much extra capacity do you need to make this learning successful. I did ask what is the right learning if I want to look at things in the long-term success, which I think we have some evidence with the Nash result that long-term success is a better way to look at things. And then maybe last but not least, or definitely maybe most importantly, this is a toy model of queuing theory. Definitely should ask what are other games where this kind of analysis is possible. I definitely, if you think of packet routing in the internet, it's not servers and queues, but multiple routers stacked after each other. If I want to go back to the budgets and auctions, then that has a similar carryover effect. If you won in an auction, you have less money. If you lost, you have more money. So can we extend these results to budgets? Can we extend it to more complex queuing theory systems? Those are all nice open questions, and I'm going to stop here and thank everyone for your attention.
Thank you so much, Eva, for a real nice talk. I see that there's one question in the chat. I'm going to unmute Eduardo so that he can ask his question. And after that, I have a question as well. For the rest of the audience, if you have questions, either raise your hand or type them in the chat. Eduardo, you should be able to talk right now. You can unmute yourself and ask your question.
Thank you. Thank you for your presentation, Eva. My question is, how much time do you think that the stability needs to occur?
So the bands we prove are on how high the Qs get in expectation. So I guess if I take my overall band on the Q sizes, I guess that implies a band on your question that is Q sizes one, after like how long does it take the Q to even grow that long? I haven't asked myself, or we haven't asked ourselves exactly the question you're asking, so I'm not, I don't know if I can offer you a better band than what's implied by the theorems we actually have, which are banding the Q sizes. I should also add that the actual bands in the paper, worked at in the paper, are worked at for assuming the worst kind of learning algorithm with the root T regret band. And I have said this, and I do believe it, but I have not worked out the details and mathematical details for this, is that if I give you more information, the learners can learn with a smaller regret error, which of course then would lead to lesser Q sizes. Because basically what you're waiting on the time horizon is that the regret error shouldn't dominate the term. Like there's a regret error, there is your success rate minus the regret error. Initially, the regret is bigger than your term, so you're not necessarily getting anywhere.
I get you. Thanks for your answer.
I have a quick question, Eva. So I like this dichotomy between oldest first and the uniform policies, and how oldest first facilitates some coordination. And I guess one could also consider some other protocols that would incentivize better coordination on the side of the server. For instance, suppose that if there's a conflict at the server bans all submitting queues for a random amount of time, or something along those lines. And I guess this is kind of analogous to pricing in congestion games to improve welfare. You could think about servers doing something smart so as to better facilitate coordination. Any thoughts on how one could think about these type of policies, and how the factor of 1/2 could be adapted to those settings?
I certainly haven't thought about, or I don't know answers to your second question, whether I can adopt the factor of 2, and I can sort of ask you back some, clarifying or some questions.
Sure.
Of the form of, based on what information? If the queues are the servers are centrally coordinated, and they know all the arrival rates of all the queues, maybe it's possible to get them to do the optimal thing. I'm not sure.
I wasn't really assuming that servers know much about the queues, aside for the fact that at any period I know the IDs of the queues that submit the jobs.
Yeah.
And if I know that,
so it's more interesting if it's without so much knowledge. But I guess good question. I don't know.
And there's one other question which is of different flavor that I had, but maybe if audience has a question, I'll wait. If not, I'll just ask my other question, if you don't mind. Don't see any more hands up, so let me just ask my other question, which goes back to my first question in the talk. Like, if I had an additional bipartite graph structure, like something that tells me about which queues can submit jobs to which servers on the other hand, on the other side. I suspect that similar positive results about no-regret learning could be obtained. I'm not sure if the factor would be 1/2. I can't tell if the results or the approach immediately would generalize to such settings or not. If you have any thoughts on that, um, I would love to hear that. And I guess related to this, another thing that is really unclear to me is what the impact of a network structure in such a setting would be. If I have a dense bipartite graph, then I guess effectively the stability region is larger. Like in the coordinated setting, I can do better if the graph is dense. On the other extreme, this may lead to more congestion, or this may make coordination harder. So qualitatively, it's not clear how things will change as the graph gets denser.
Yeah, you're definitely asking great questions that I have some suspicion, but I wish I knew the answer better. The benchmark, that is how much capacity do you need to actually get everything across, is the natural extension of what I wrote. It's a I guess a whole theorem-like condition.
Right.
Like every subgroup of queues should have enough capacity.
Yeah.
But the capacity should not come, like enough capacity, but has to come with at most as many servers as they are, right? A subset of 7 queues can only use 7 servers, so it should come from those whatever some subset of 7 servers. I suspect the factor of 2 will extend, but I guess I wish I knew it better. The denser graph, I guess I didn't even begin to think about. I guess when I was thinking about the graph extension, I really meant not a random graph, but a worst case graph.
Yeah, I guess when I use the word dense, I use it a little bit loosely. I mean, I'm thinking about the deterministic graph, but fix the nodes. I have a set of edges. What would happen if I were to go from this to a subset of edges? I guess on one hand, if I just think about the coordinated system, in the coordinated system, removal of the edges should make coordination, sorry, they should decrease the stability region. But at the same time, it makes coordination easier in a way. So these are two competing effects, and I can't tell which way things will go.
Oh, I see. That's an excellent point. There's definitely the usual kind of paradox here. Maybe my best, cleanest way to tell you about it is based on the uniform selection example, where I claim that the factor of 2 tight band is coming from a very similar example, a bit more carefully coordinated. In these examples, to prove feasibility or prove that we have the sufficient gap to meet feasibility even with decreased server capacity, is coming that everyone has their own server. Like you might remember, and I can page back to that slide, every queue had a personal server. So if I only allow them to go to their own server, we know they're okay, because that was my feasibility assumption. If I allow them to go to every server, they unfortunately kill each other.
Right, I see.
So the fact that subset can be, that offering them more options can actually hurt them, oh yeah, definitely. Like remember, that was the example. If I don't allow them to do that red thing, and they have to go to what the black arrow suggested, then it's perfect. That was set up that way. And unfortunately, if I give them more options, selfishly, they're going to do the wrong thing.
Yeah, I see.
So definitely, taking a subgraph can make things better. Or giving them more options can make things worse.
So this is very good. In the meantime, I see that there's one other question in the chat. Let me relate to you. How is the size of the carryover effect quantified? Would this inform us on the suboptimality of a no-regret benchmark?
Yeah, nice question. And honestly, I don't know the answer to either one of them. So what I said about carryover effect is that this is a general open area. And what we're offering here is one example of a game with a natural carryover effect. And that's it. That is, but I'm not being able to offer a general theory of carryover effect, measuring carryover effect, or generally saying how big or what is a important carryover effect and what is not. So I guess this is a beautiful question, and I would, whoever the anonymous questioner is, if you have results on this or even ideas, please do let me know.
Very good. I think this is all the questions we had, Eva. I don't see any more open questions or hands up. So thank you so much for the super nice talk. This was great. And thanks again for taking the time despite the EC deadline.
Well, I should thank the audience for showing up despite the easy deadline. And I wish everyone good luck in finishing everything before the deadline hits at midnight, or at least midnight my time zone.
Thank you very much. And
thank you very much, Eva. That was great.
Thank you.
Thank you.
Okay, thank you to
Thank
both
you
of you.
again. Thank you again, Eva. That was very,
That's
very
okay.
good. Thank you. Yeah,
Cool.
great. And again, we really appreciate it. I know it's a very busy time for you, both as a head and also as a computer science thing pushing deadline for you. See, thanks again.
Okay, thank you.
All right.
Nice to meet you.
Have a good weekend.